James Webb just uncovered something that challenges everything we thought we knew about the shape of the universe. Galaxies too heavy, too organized, and too old are appearing in its images by the thousands. They have no business being there. The standard picture of the cosmos, constructed from centuries of careful observation, told us space was flat, vacant, and limitless in every direction. The data is telling a different story. Space might bend. It might fold back on itself. The universe could possess a definite form. We are going to examine ancient light concealing impossible contradictions, a team chasing the geometry of space itself, and a cosmos that might be bounded, curved, and dramatically smaller than anything we can observe. If this reaches inside your skull and rearranges something, like and subscribe. Get ready. We start now. The universe is either the most giving thing that has ever existed or the most cunning. It has handed humanity billions of years of stellar radiation, allowed us enough time to raise civilizations and construct observatories, and still withheld the answer to the one question that matters above all others. Does it terminate? Aristotle posed that question around 350 years before the Common Era. He was not being figurative. He wanted to understand whether space itself had an end point, whether there was some location where the cosmos ceased and something else took over, or whether it persisted without center, without boundary, without any conclusion. He never found the answer. He had no instruments capable of revealing it. Nobody did. For the overwhelming majority of recorded human history, the question of the universe's shape was treated as philosophical territory, perhaps even theological ground, and categorically beyond the reach of any experiment a person could actually conduct. That situation transformed in the 20th century, and it transformed because two ideas emerged almost at the same moment. The first was Albert Einstein's general theory of relativity, published in 1915. Before Einstein, space was regarded as a fixed and passive container, the backdrop against which matter acted out its drama. After Einstein, space became something entirely different. It curved. It responded to mass and energy by bending. It could stretch or compress. It possessed a geometry that was in principle accessible to measurement. The universe was no longer a neutral stage. It was a physical entity with its own intrinsic shape, governed by precise mathematical equations. The second instrument was the telescope, and more specifically, the increasingly powerful machines astronomers assembled across the 20th century to examine the most ancient light in existence, the cosmic microwave background. This is the faint haze of radiation surviving from 380,000 years after the Big Bang, when the universe had cooled enough that photons could travel freely for the first time. This primordial radiation pervades every direction of the sky and carries within it a detailed archive of what the cosmos looked like in its earliest configuration. The structure of this radiation encodes information about the geometry of space at the deepest level. Together, general relativity and the cosmic microwave background provided cosmologists with a mechanism to pose Aristotle's question in numerical terms. They could quantify the curvature of space. They could determine whether the universe was open, closed, or geometrically flat. They could, in principle, map the shape of everything. For several decades, those measurements converged on the same response. The universe is flat, infinite, and structurally featureless at the grandest scales. The standard cosmological model was erected on that conclusion. Most textbooks treated flatness as essentially settled. Then the James Webb Space Telescope launched in December 2021, and the data it began transmitting was unlike anything the cosmological community had anticipated. Galaxies that should not exist at all. Structures that coalesced too rapidly, too early, and too massively. An early universe bearing no resemblance to what the simulations had calculated. Something had broken inside the model. And if the model had broken, then the assumptions embedded within it, including the assumption about the fundamental shape of the universe, demanded reconsideration. This documentary concerns that reconsideration. It addresses the shape of the cosmos, whether space curves back on itself like a globe, expands outward perpetually like a saddle, or folds around in configurations so strange that human language has barely begun to develop the vocabulary to describe them. It begins, as all consequential questions begin, with geometry. To grasp what cosmologists mean when they discuss the shape of the universe, you first need to set aside the ordinary meaning of that word. A ceramic mug has a shape. A hillside has a shape. These are objects situated inside space, and you can circle them and survey their contours from an external vantage point. The universe has no exterior. There is no position from which an observer can step outside and examine the whole. Everything that can be seen is seen from within, and this creates a distinct methodological problem. The only way to measure the shape of space is to study the behavior of things contained inside it. Albert Einstein's general theory of relativity hands you the equipment to do exactly this. Within his framework, the curvature of space is a physical reality that governs how objects move, how light travels across it, and how geometric angles combine. The geometry of space is real, measurable, and determined by the matter and energy it contains. Three possibilities exist, and they diverge from one another in fundamental ways. The first is a positively curved universe. Picture the exterior of a sphere. Mark two lines on it that begin perfectly parallel, like two meridians drawn at the equator. As you trace them toward the poles, they draw closer. They eventually meet. In a positively curved space, lines that intuition says will never touch end up intersecting. Draw a triangle on the surface of a globe, and its three interior angles sum to more than 180 degrees. This variety of space is described as closed, and it curves back on itself the way a spherical surface does. The second possibility is a negatively curved universe. Rather than a sphere, picture a saddle, the kind used on a horse, curving upward along one axis and downward along another. In a negatively curved space, parallel lines diverge from each other rather than converging. A triangle drawn in such a space has interior angles summing to less than 180 degrees. This type of space is called open, and it flares outward continuously without ever looping back on itself. The third possibility is a flat universe. This is the geometry taught in secondary school. Euclidean geometry, where parallel lines remain parallel indefinitely, where a triangle always encloses exactly 180 degrees, and where space extends in every direction without bending. It is the intuitive and familiar geometry of everyday experience. Cosmologists evaluate which of these three geometries characterizes our universe using a parameter they designate omega k. When omega k equals 0, the universe is flat. When it is negative, the universe is positively curved and closed. When it is positive, the universe is negatively curved and open. The more closely omega k approaches 0, the flatter the spatial geometry. The primary instrument for measuring omega K is the cosmic microwave background. The ancient light from the early universe carries millions of minute temperature variations, hot regions and cold regions distributed across the entire sky. The apparent size of those fluctuations is exquisitely sensitive to the underlying curvature of space. Light traversing curved space follows curved trajectories, which expands or contracts the apparent scale of features in the background radiation. Cosmologists take those size measurements, compare them against theoretical predictions, and extract the geometric character of the cosmos. When the measurement came in, it appeared to resolve the debate. But resolved, it became clear, was the wrong description. In 2009, a spacecraft assembled by the European Space Agency launched the most precise survey of the ancient light of the cosmos ever attempted. It was known as the Planck satellite, named after the German physicist Max Planck, and it spent 4 years charting the cosmic microwave background with sensitivity and angular resolution that previous instruments had only approximately achieved. By 2013, it had accumulated enough data to construct a detailed portrait of the sky at the moment the universe first became transparent, a snapshot captured 380,000 years after the Big Bang. What Planck uncovered when researchers processed the complete dataset appeared to validate the standard account. The cosmic microwave background matched the predictions of the flat universe model with remarkable precision. Cosmologists across the globe published papers treating the curvature question as essentially settled. The universe was flat. The standard model had passed its test. Then a research team tried something subtly different. They examined the Planck data in isolation, deliberately setting aside the additional measurements gathered from galaxy surveys. What they found was unexpected enough to halt the conversation. When the Planck data was analyzed without supplementary inputs, the best statistical fit to the observations pointed toward a universe with positive curvature. The omega K parameter, extracted purely from the Planck satellite data using standard statistical methodology, came out at negative 0.044, with an uncertainty of approximately 0.016. That negative value meant the universe was bending back on itself, closed, and the signal was strong enough that random noise could not comfortably account for it. The statistical confidence reached approximately 3.4 sigma, meaning the probability of obtaining a result that, far from zero through chance alone, was less than 1 in 1,000. The researchers behind this finding were Eleonora Di Valentino of Sheffield University, Alessandro Melchiori of Sapienza University in Rome, and Joseph Silk of Johns Hopkins University and Oxford. Their paper ran in the journal Nature Astronomy in 2019 and advanced a specific and uncomfortable conclusion. The Planck data, they argued, favored a closed universe at 99.985% probability. To appreciate why that conclusion was so alarming, you need to understand what a closed universe entails. In the standard cosmological model, the universe is flat because cosmic inflation, the period of extraordinarily rapid spatial expansion in the first tiny fraction of a second following the Big Bang, stretched any initial curvature away, precisely as the surface of a balloon begins to look flat when you inflate it to enormous size. The universe should likewise have had its curvature erased by that inflationary episode. Detecting substantial curvature would require either that inflation never unfolded in the manner the standard model describes, or that the universe began with extraordinary curvature to begin with, or that something else entirely was generating the measured signal. There was also a specific physical mechanism explaining why the Planck data preferred a closed universe. The sky maps showed a moderately stronger than expected signal from gravitational lensing, the deflection of ancient light by intervening matter as it traveled toward us. A closed, positively curved universe would contain greater matter density and generate proportionally more gravitational lensing. The observations fit that picture more naturally than the flat alternative. The immediate question that arose was obvious. If the universe is closed according to Planck, why does every other measurement insist it is flat? Untangling that contradiction would require years of work, and it remains incompletely resolved today. Cosmology advances through convergence. The great achievement of the Standard Model was that dozens of independent measurements employing completely different physical phenomena converged on the same values for the fundamental parameters of the cosmos. Galaxy clustering surveys, the cosmic microwave background, observations of distant supernovae, the primordial abundances of light chemical elements, all of them assembled a mutually consistent account. That consistency was the basis of the model's credibility. So, when Di Valentino and her colleagues announced that the Planck satellite data in isolation preferred a closed universe, the immediate response from the broader cosmological community was to cite the other measurements, in particular the measurements of something called baryon acoustic oscillations. Baryon acoustic oscillations are a regular, periodic pattern in the spatial distribution of galaxies throughout the cosmos. They originate in sound waves that traveled through the hot, ionized plasma of the early universe, leaving behind a characteristic scale imprinted in the clustering of matter at every location. That scale functions as a cosmic measuring rod. By quantifying the apparent angular size of baryon acoustic oscillations at various distances, astronomers can determine the geometric properties of space. When the Planck data was combined with baryon acoustic oscillation measurements from large galaxy survey programs, the curvature estimate shifted radically. The omega k value moved from negative 0.044 to essentially zero, specifically to negative 0.0007, with an uncertainty of roughly 0.0019. That figure was indistinguishable from a perfectly flat universe. The two datasets, each individually trusted and painstakingly calibrated, produced wildly inconsistent answers when each was used alone, and only agreed when merged together. This inconsistency is called a tension, and it has not diminished with time. In 2024, researchers published the definitive analysis of the Planck satellite data, a comprehensive revision led by Matthew Tristram and collaborators working in Paris. The updated analysis employed improved techniques and reduced the contribution of systematic measurement errors. The curvature estimate from this refined dataset softened compared to the earlier finding. Omega k settled at negative 0.012, with an uncertainty of roughly 0.010. Still slightly negative, still tilting toward positive curvature, but now consistent with flatness at approximately 1.2 sigma rather than 3.4. That sounds like encouraging news for the flat universe interpretation, and in one sense it genuinely is. The case for a dramatically closed cosmos has softened with better data. But the hint has persistently declined to vanish. The central value of omega k in the most recent analysis remains negative. It continues, pointing toward closure. It simply does so with less urgency than before. The present state of the measurement is genuinely unresolved. Considered alone, The best Planck data leans toward a slightly closed universe. Combined with galaxy survey measurements, it is consistent with flatness. Other independent experiments, including the Atacama Cosmology Telescope and the Dark Energy Spectroscopic Instrument Survey, deliver results consistent with zero curvature, but with error margins broad enough to encompass the Planck suggestion. Nobody can claim with certainty that the universe is precisely flat. What nobody has managed to do is prove that it is. The curvature question remains open, and it remains open in a way that carries real consequences, because curvature represents only half of the larger problem. The other half is something most cosmologists rarely discuss, and it changes the entire picture. Everything described so far about the flat universe, the closed universe, and the measurement of curvature belongs to geometry. It concerns the way angles combine, the behavior of parallel lines, and the bending of light. It is the portion of the question that physicists have developed instruments to address. But there is a second component of the universe's shape problem that geometry cannot resolve independently, and it is arguably the more fundamental part. That second component is topology. Topology and geometry address different aspects of spatial structure. Geometry describes the local properties of space, whether it curves and in which direction. Topology describes the global architecture, how the entire universe connects to itself at the largest conceivable scales, whether a traveler could move in a straight line indefinitely and eventually return to the exact point of departure. The critical realization is this: you can inhabit a universe that is geometrically flat, that satisfies every requirement of Euclidean geometry, that yields perfect 180-degree triangles wherever you draw them, and that still folds back upon itself in a manner that makes it finite in total volume. The most transparent way to see this is with an ordinary piece of paper. A flat sheet of paper has zero curvature. Now roll it into a cylinder and connect the two open edges to form a tube. The surface of that cylinder remains locally flat in every measurable way. Triangles drawn on it still sum to 180 degrees. Parallel lines drawn on it still stay parallel. Yet the global architecture has transformed entirely. Walk along the surface in one direction, and you will eventually return to your starting position. The space is finite, and it wraps. Despite the fact that local measurements reveal nothing unusual, nothing that deviates from standard flat geometry at all. Take that cylinder further, bending it until the remaining open edges connect, and you obtain the shape of a donut. Mathematicians named this configuration a torus, a three-dimensional analog of a torus, where the universe wraps around itself in all three spatial directions simultaneously, is called a three-torus. It represents one of the simplest possible compact topologies for a universe to have. In a three-torus universe, a traveler moving in any fixed direction long enough would eventually arrive back at the original starting location, approaching from the opposite direction. The universe would be finite in total volume, and yet it would possess no boundary whatsoever. This possibility lies entirely within the mathematics permitted by general relativity. Glenn Starkman of Case Western Reserve University, one of the foremost researchers working on this problem, has spent years arguing that it warrants serious scientific attention. He has maintained that cosmologists could pass by an extraordinary discovery simply by looking the other direction, by assuming without empirical justification that the simplest conceivable topology is the correct one. The standard cosmological model assumes the universe is simply connected, meaning it contains no wrapping or folding of any kind. That space extends outward in every direction without looping back. This assumption rests on parsimony and Occam's razor. In the absence of contrary evidence, assume the simplest available case. Measuring curvature near zero does not validate that assumption. A flat measurement of omega k informs you that space does not curve dramatically within your observable neighborhood. It provides no information whatsoever about whether space folds around at distances far beyond what any telescope can survey. The topology of the universe and the geometry of the universe are distinct questions requiring distinct methods to answer. And the evidence for a non-trivial topology, it turns out, has been embedded in the data all along, waiting to be recognized. There exists a concept that mathematicians developed long before cosmologists found any need for it, and it ranks among the most genuinely disorienting propositions in all of science. A space can be finite without possessing any boundary. It can have a definite total volume, a quantifiable size, and yet contain no edge that could be reached, no wall against which a hand could press, no precipice from which one could peer outward into anything else. The space simply connects onto itself, the way the surface of the Earth connects onto itself, and every straight path eventually circles back around. The surface of the Earth is the standard illustration, and it holds up well. Walk in a single direction long enough on a perfectly smooth spherical Earth, and you will encounter no edge. You will arrive back where you began. The surface is finite in area, roughly 197 million square miles, but it has no boundary at all. This analogy extends to a three-dimensional universe. If space wraps around in 3 dimensions, any traveler moving along a fixed trajectory would eventually arrive home, approaching from the direction diametrically opposite the one they originally headed in, having circled a cosmos that contains no walls anywhere. Mathematicians have enumerated all the distinct ways a three-dimensional geometrically flat space can fold back on itself. There are 18 separate possibilities, 18 different topological configurations that preserve flat geometry while being multiply-connected in structure. The most basic is the 3 torus, where you picture a cube of space and specify that the left face connects to the right face, the ceiling connects to the floor, and the front face connects to the back. A universe with this architecture would be finite in volume, equal to that fundamental cube, and it would repeat periodically. Whatever you saw looking leftward would eventually cycle back around to what exists behind you. Other flat topologies are more elaborate. Some incorporate twists. In a half-turn torus, opposite faces of the cube are joined after a rotation of 180 degrees, so that crossing one boundary flips your orientation. You return to your point of departure, but left and right are exchanged. You arrive as your own mirror image. Quarter-turn versions exist as well, along with stranger configurations combining multiple rotations and reflections. All of them preserve the flat geometry that every measurement suggests our universe possesses. The observational signature of any such topology would be distinctive and identifiable. If the universe's fundamental domain, the basic spatial unit that repeats, is smaller than the observable universe, then identical physical objects would appear multiple times across the sky, captured from different viewing angles at different cosmic epochs. A distant galaxy cluster visible on one side of the sky might represent the same physical cluster imaged from another direction billions of years later or earlier on the opposite side. the universe would appear larger than it actually is. A hall of mirrors in which a limited spatial region projects the illusion of boundless extent. The decisive question is whether the fundamental domain is compact enough that its multiple reflections fall within telescope range. If it is larger than the observable universe, those echoes would never arrive at all. If it is smaller, they should be detectable, imprinted on the oldest photons in existence, waiting for an observer who recognizes them as duplicates. Two separated patches of sky displaying identical patterns. That is the signature to hunt. In 1998, 3 cosmologists published a paper that fundamentally redirected how researchers thought about the universe's shape. Neil Cornish, who subsequently moved to Montana State University, David Spergel at Princeton University, and Glenn Starkman at Case Western Reserve University had derived a specific testable prediction for what a multiply-connected universe would look like when observed from within. Their reasoning began with the cosmic microwave background and a straightforward geometric insight. The surface of last, scattering the spherical shell of ancient photons we observe as the cosmic microwave background, is a vast sphere centered on Earth with a radius of roughly 46 billion light-years. That sphere marks the observational horizon, the outermost limit of what we can perceive. Any light that departed from regions farther than 46 billion light-years away simply has not had sufficient time to reach us. Now, suppose the universe's fundamental domain, its smallest repeating spatial unit, is smaller than that sphere. The sphere of last scattering would then extend beyond the boundaries of that fundamental unit and wrap around inside it. It would intersect itself, and wherever it intersected, 2 separate patches of sky would actually represent the same physical location in the primordial universe, simply observed from different directions. Those 2 patches, Cornish, Spergel, and Starkman recognized, would exhibit identical temperature signatures. The same hot regions, the same cold regions, the same fluctuation patterns because they are physically the same location. The temperature structure of the cosmic microwave background is a physical phenomenon, a map of density variations in the earliest plasma. If 2 circular regions of sky correspond to the same ring of points in that original plasma, those regions must be mirror images in temperature. The researchers titled their paper "Circles in the Sky." The test they proposed had an elegant simplicity. Scan the complete sky map of the cosmic microwave background, searching for pairs of circles whose temperature profiles match. If you locate them, you have found the topological fingerprint of a finite multiply-connected universe. If you find no matching circles beyond what random variation predicts, the universe's topology is either too large to detect or simply connected throughout. The implications of actually finding matched circles would be profound. It would mean that a substantial portion of what we observe in the night sky is the same physical region of space appearing repeatedly, seen from different directions at different moments in cosmic history. The hundreds of billions of galaxies distributed throughout the observable universe might represent a far smaller number of actual distinct galaxies, each replicated over and over by the repeating topology of space. Our cosmos would be a vast hall of mirrors, a limited spatial region projecting its image in every direction, generating the impression of an infinite and unrepeating expanse when the underlying reality was something far more compact. The search commenced immediately. Astronomers applied the technique to data from the Wilkinson Microwave Anisotropy Probe satellite, then to data from the Planck satellite. The results were intriguing, disputed, and ultimately inconclusive. Certain analyses found indications of matched circles. Others found nothing statistically compelling. The debate generated considerably more controversy than clarity across nearly 2 decades. But while that debate continued, something else was accumulating in the background. The cosmic microwave background had started displaying patterns that no one had anticipated. Patterns that continued reappearing in dataset after dataset, even as instruments grew progressively more sophisticated. And those patterns were profoundly strange. In autumn of 2003, a team of 5 researchers published a paper in the journal Nature that advanced one of the most specific and striking answers to the shape of the universe ever to appear in peer-reviewed literature. The lead author was Jean-Pierre Luminet, a cosmologist at the Observatoire de Paris. His collaborators included Jeffrey Weeks, an independent mathematician from upstate New York, together with Alain Riachuelo, Roland Lehoucq, and Jean-Philippe Uzan. They argued collectively that the universe might have the shape of Poincare dodecahedral space. This requires some unpacking. A dodecahedron is a 12-faced solid, each face a regular pentagon. In ordinary 3-dimensional space, you can construct one from cardboard and examine it directly. The Poincare dodecahedral space is something fundamentally different and far stranger. It is what you obtain when you take a spherical version of that dodecahedron, one whose faces are slightly curved because the underlying space itself is positively curved, and specify that each of the 12 pentagonal faces is identified with the face positioned directly opposite it, following a rotation of 36 degrees. The resulting space is closed, finite, and strikingly counterintuitive. Its volume is roughly 80% of the volume of the entire observable universe. This means the universe, if it has this topology, would actually be smaller than the sphere of sky we can observe. The surface of last scattering would extend beyond the boundaries of the fundamental dodecahedral domain and fold back on itself, intersecting in 6 pairs of matched circles. Each pair would exhibit identical temperature patterns because each maps to the same ring of points in the primordial plasma, but rotated relative to each other by exactly 36 degrees. What motivated Luminet and his colleagues was observational data. The initial maps from the Wilkinson Microwave Anisotropy Probe satellite had been released that year, and they contained an anomaly. The largest scale fluctuations in the cosmic microwave background, the so-called quadrupole and octupole modes, were substantially weaker than the standard flat infinite universe model predicted. The universe simply lacked the large-scale power it was supposed to have. The Poincare dodecahedral space offered a natural account of this deficit. In any finite space, the topology acts as a constraint on what oscillations are permitted to exist. Just as a taut string can only generate waves with wavelengths up to twice the string's length, a finite universe can only accommodate oscillations that fit within its fundamental domain. A Poincare dodecahedral space with a volume around 80% of the observable cosmos would automatically suppress the largest modes, cutting off power at precisely the angular scales where the probe had found it depleted. The paper triggered a scientific dispute that persisted for years. Some researchers who searched for the predicted matched circles found hints consistent with the dodecahedral model. Others conducted independent searches and found nothing worth reporting. Bałdywan Rukema at Nicolaus Copernicus University in Torun, Poland, led several detailed analyses of the probe data and identified tentative evidence for 6 matched pairs at an angular radius of approximately 11 degrees, consistent with the dodecahedral model's specific predictions. The probability his team calculated of that signal arising by chance in a simply connected flat universe was only 7%. 7% is suggestive. It is nowhere near conclusive. The soccer ball universe remained a live candidate, one of the most mathematically attractive proposals in modern cosmology, with partial observational backing and fierce opposition, occupying equal space in the community's attention. And, while the dispute continued, the cosmic microwave background was accumulating further anomalies that nobody had requested and nobody could adequately explain. Anomalies in science are uncomfortable things. They appear in data that researchers were not expecting, survive the first wave of checks for measurement error, survive the second round of inspection for software problems, and then simply persist, unresolved, while the community deliberates whether to treat them seriously or hold out for better data that might make them vanish. The cosmic microwave background has collected several such anomalies over the past 20 years. They did not dissolve with better data. They intensified. The most widely discussed of these is called the quadrupole-octupole alignment. In a universe that is statistically uniform in all directions, the fluctuation patterns at different scales in the cosmic microwave background should point in random orientations with no preferred axis. The quadrupole, the longest wavelength pattern in the background, and the octupole, the next largest scale below it, should have their respective orientations scattered without correlation. When the Wilkinson Microwave Anisotropy Probe satellite returned its initial maps in 2003, researchers noticed that the quadrupole and octupole were aligned with one another, pointing in nearly identical directions across the sky, their orientations separated by no more than 11 or 12 degrees. Cosmologists Kate Land and João Magejo named this preferred axis the axis of evil in 2005. The probability of this alignment arising by chance within the standard model is less than 1%. The Planck satellite was supposed to settle this. It was more sensitive, possessed finer angular resolution, and was capable of identifying systematic instrumental errors that earlier detectors might have missed. When the Planck maps were subjected to careful analysis, the quadrupole-octupole alignment remained. It had survived a new generation of instruments. The second anomaly involves the angular correlation function, a statistical tool measuring how strongly temperature fluctuations are related across different angular separations on the sky. In the standard infinite flat universe model, fluctuations should be correlated at all angular scales, including large separations spanning more than 60 degrees. The actual data shows something categorically different. For angular separations exceeding roughly 60 degrees, the correlation essentially collapses to zero. The two hemispheres of the sky become thermally uncorrelated at large scales in a way that cannot occur if the universe stretches infinitely in all directions. A third anomaly also exists. The two hemispheres of the cosmic microwave background sky are not equivalent. One carries roughly 6% more power than the other. The northern and southern halves of the sky are measurably asymmetric, indicating that the universe does not look identical in all directions, which the standard model explicitly requires. In 2024, a research team led by Gabriel Jung and Nabila Aghanim published a careful analysis of these anomalies using the final Planck data release. Their verdict was unambiguous. These features appear at a level found in typically less than 1% of simulated cosmic microwave background maps produced by the Standard Model. They survive updated examination with refined noise models and corrections for systematic instrumental effects. They are not artifacts. They are physically real. The combined probability that all these anomalies appear simultaneously in a universe described by the Standard Model is less than 1/10 of 1%. Physics does not casually generate results that improbable without reason. Either something is wrong with the analysis methodology, or something is wrong with the underlying model, or the cosmos is communicating something specific about its own structure. A finite universe with a characteristic spatial scale would naturally suppress large-scale power above a specific threshold. That suppression is precisely what the measurements reveal. Something still more peculiar lies waiting in the southern sky. Among all the anomalies recorded in the cosmic microwave background, one is in a class of its own. It has a specific location on the sky. It has a well-defined angular diameter. It has a measured temperature. And it has so far resisted every effort to account for it within standard cosmological physics. Researchers refer to it simply as the cold spot. It sits in the southern sky in the direction of the constellation Eridanus. The cold spot spans approximately 5 degrees in angular diameter, which sounds modest until you realize that in sky terms it is enormous, 10 times the apparent width of the full moon. Within that angular region, the cosmic microwave background is cooler than expected by roughly 150 microkelvin. That number sounds vanishingly small because it is. The cosmic microwave background varies in temperature by only around 100 millionths of a degree across the entire sky. The cold spot represents a deviation at the lower end of that already minuscule range. But the statistical significance makes it impossible to dismiss. The probability of finding a feature that extreme, that large, and that cold in a standard simulation of the cosmic microwave background is below 1%. The cold spot was first identified in Wilkinson microwave anisotropy probe satellite data and was immediately recognized as demanding an explanation. The most straightforward hypothesis was that a large underdense region of space, a supervoid, was positioned along the line of sight between us and that portion of the last scattering surface. As photons traverse a void, the universe's accelerating expansion induces a small temperature shift through a process called the integrated Sachs-Wolf effect. A sufficiently large and deep supervoid could stamp a cold signature onto the background radiation. Researchers went to search for the supervoid. They found one. A substantial region of space in the direction of Eridanus does appear to be depleted in galaxies relative to the surrounding environment. But when astronomers computed how cold a feature that supervoid should generate, the numbers fell short. The void is not large enough, not deep enough, and not sufficiently empty to account for the full anomaly. It contributes some fraction of the observed signal, but leaves the remainder unexplained. Other proposals have been advanced. A topological defect originating from a phase transition in the very early universe could leave a cold impression in the background. Such defects, sometimes called cosmic textures, form when a field that was uniform in the hot primordial plasma breaks into distinct configurations as the universe cools, and the interfaces between those regions can scar the radiation. The mathematics permits it. The observational evidence for it is indeterminate. Then there is the most striking suggestion of all. The cold spot is a scar left by a collision between our universe and another. Within the framework of eternal inflation, The space outside our observable bubble is a churning landscape of perpetually inflating vacuum, intermittently giving rise to other bubble universes that expand in isolation. If two such bubbles had collided at some point in the remote past, the collision would have imprinted a circular mark on the cosmic microwave background of the surviving universe. Models developed by Stephen Feeney, Matthew Johnson, Daniel Mortlock, and Hiranya Peiris in 2011 demonstrated that such collision scars would manifest as circular disc-shaped anomalies in the background radiation. The cold spot is roughly circular and disc-shaped in morphology. None of the proposed explanations is fully adequate. The cold spot remains without a definitive explanation. It occupies its position in the southern sky, colder than everything around it, larger than it should be, resisting every framework developed to account for it. And it is not alone in this resistance. The cosmos has been accumulating evidence against its own standard description for decades. The James Webb Space Telescope has since added the most dramatic piece of that evidence. The original test for cosmic topology had a conceptual elegance. If the universe folds back on itself, a specific fingerprint should be encoded in the most ancient light we can observe. Two separate patches of the cosmic microwave background, separated by enormous angular distances across the sky, should bear identical temperature fluctuation patterns, because they would represent the same physical location seen from different vantage points. Astronomers named these predicted mirror image patches matched circles. In the early 2000s, the IT competition to identify them began in earnest. Budowijn Rukema at Nicolaus Copernicus University in the Polish city of Torun led one of the most sustained searches. He methodically worked through data from the Wilkinson Microwave Anisotropy probe satellite, comparing region after region of ancient sky against every other region. Every direction had to be tested against every other direction, at every possible angular scale, across an entire sphere of photons that had been traveling for nearly 14 billion years. The computational requirements were staggering. The potential implications felt enormous. Then something materialized. Rukema's team identified tentative evidence for 6 matched pairs of circles, each pair positioned at an angular radius of roughly 11 degrees. Their geometric arrangement was consistent with the Poincaré dodecahedral space that Luminet had proposed only a few years earlier. The statistical evaluation was honest and rigorous. The probability that this signal arose by accident in a simply connected flat universe was 7%, suggestive and tantalizing, but inadequate to settle the debate definitively. Neil Cornish at Montana State University conducted a different search. He scanned for matched circles larger than 25 degrees across the complete sky and found none at those angular scales. His team concluded the dodecahedral universe was ruled out. But there was a gap in the coverage between the two searches that almost no one noticed at the time. Rukema had found hints at 11 degrees. Cornish had searched above 25 degrees. The angular range between those two thresholds, the very territory where a genuine signal might plausibly reside, had never been examined at all. The map had a hole in it, and nobody had drawn attention to where the hole was. The controversy continued for years following this exchange. Later releases of the Wilkinson probe data arrived, and Rukema re-evaluated his findings each time. The signal persisted, weaker in some analyses and stronger in others, but it never reached the threshold needed to silence the skeptics. Both groups were doing careful, principled science and arriving at divergent conclusions from identical observations. That tension was itself worth examining closely when the European Space Agency's Planck satellite delivered its comprehensive survey of the cosmic microwave background. The topology question received another formal review. The Planck collaboration established in 2016 that if the universe has dodecahedral or torus topology, its fundamental domain must be larger than roughly 97% of the diameter of the last scattering surface. That sounded definitive for the specific shapes tested, at the specific positions assumed, and in the specific orientations examined. The critical phrase there is the positions they assumed, and that is precisely where complications arise. Topology searches require prior knowledge of where the observer is located inside the universe's fundamental domain. Different positions within that domain produce entirely different patterns of matched circles. The Planck searches examined certain positions thoroughly and others hardly at all. Rukema and his colleagues noted this explicitly. The constraints were genuine, but they were not exhaustive. A dodecahedral universe oriented somewhat differently or scaled differently could be concealed in the data without generating any detectable signature. The matched circles search had exposed an unexpected asymmetry. Detecting matched circles was difficult. Not detecting them did not constitute proof of their non-existence. If the universe was wrapped, it was being remarkably careful about disclosing its own structure. And the team that would extend the search beyond what anyone had previously attempted was only beginning to assemble. In 2022, roughly 15 scientists distributed across 7 countries began collaborating on a problem that most of the cosmological community had quietly abandoned. They named their group the Collaboration for Observations, Models, and Predictions of Anomalies and Cosmic Topology. The name compressed into the acronym COMPACT. The ambition embedded in that name was anything but modest. Glenn Starkman, at Case Western Reserve University in Ohio, had spent multiple decades urging colleagues that topology was being systematically overlooked. He had co-authored the original Matched Circles paper in 1998. He had tracked searches as they came and went, observed data quality improve and constraints accumulate, and watched the fundamental question remain stubbornly unresolved. The majority of the field had moved on and accepted a flat, infinite universe as the self-evident default. Starkman had not accepted it and had not moved on. The collaboration he helped construct included Yashar Akrami at the Instituto de Física Teórica in Madrid, and Craig Coppey also at Case Western Reserve, along with researchers from institutions distributed across Europe, North America, and beyond. What bound these scientists together was not merely shared intellectual interest. It was collective frustration with how genuinely inadequate the previous generation of topology searches had proven. Prior searches had examined a handful of specific topological configurations within limited regions of parameter space using limited computational resources. Finding no definitive evidence, they published constraints and concluded their investigations. But nobody had ever systematically calculated what fraction of the total landscape of mathematically admissible cosmic shapes had actually been examined. When the COMPACT team performed that accounting, the result was startling. The fraction was negligibly small. The space of possible cosmic topologies spans thousands of distinct configurations across different curvature classes. Science had painstakingly ruled out a small corner of that vast mathematical landscape, and the broader community had treated the effort as effectively complete. There, landmark paper appeared in Physical Review Letters in April 2024. The central conclusion was stated without hedging. Prior topology searches had examined only a tiny fraction of the mathematically possible topological configurations, and many exotic shapes remained entirely consistent with cosmic microwave background observations. The universe could be wrapped in configurations nobody had yet thought to search for. The response from the broader cosmological community was measured. Some cosmologists had moved so far beyond the topology question that the paper barely penetrated their awareness. Others acknowledged it as a genuine and consequential correction to the field's self-understanding. Oliver Philcox at Columbia University described the situation plainly when he noted that there are many possible ways the universe could be topologically connected, and that ruling them out is genuinely challenging work. What set the compact effort apart from all previous attempts was not ambition alone. It was computational capacity combined with a rigorous mathematical architecture designed for systematic comparison. A decade earlier, the calculations required to properly compare topology models against real observational data would have demanded years on available hardware. Advances in computing power and in the mathematics of cosmological statistics had made the work newly tractable. They were conducting searches that had never been attempted at all. And, in doing so, they had already discovered something the field had not anticipated. One specific topology had survived every attempt to eliminate it, even when that topology described a cosmos far smaller than the observable horizon, a universe in which space itself was twisted in a pattern that had slipped completely past every prior search, completely undetected. Understanding why it survived requires thinking about the universe as a musical instrument. The most elementary wrapped universe is the three torus. Imagine a cube of space where the left wall connects to the right wall, the floor connects to the ceiling, and the front face connects to the back face. Travel far enough in any direction, and you arrive back at your starting point, like a spaceship in a classic arcade game disappearing off one edge of the screen and reappearing from the opposite side. The geometry inside this space is perfectly Euclidean. Triangles still total 180 degrees. Parallel lines maintain their separation. The only distinction from an infinite flat universe lies in the global connectivity, the way distant regions of the space link to each other. Earlier searches had placed strong limits on this basic configuration. If a three-torus universe is smaller than the sphere of the cosmic microwave background, matched circles should appear in the data at corresponding angular scales. None were found at the relevant scales. The simple three-torus appeared to be excluded for any size smaller than roughly the distance to the last scattering surface. Then the compact team examined what happens when you introduce a half-turn twist before connecting the faces. In this modified version, opposite faces of the cube are identified after a rotation of 180 degrees. When you cross through one face and emerge from the opposite side, you arrive flipped in orientation. The geometry remains flat, still consistent with every local curvature measurement ever made. But the correlation patterns this topology generates in the cosmic microwave background are fundamentally different from those produced by the untwisted version. And those different patterns are dramatically more difficult to rule out. The compact analysis found that this twisted topology, catalogued as the second of 18 mathematically distinct flat topological configurations, remained consistent with all observational data, even when the fundamental domain was considerably smaller than the observable sphere. The explanation is subtle but significant. The twisted face identification creates correlations between spatially distant points, but those correlations appear in statistical forms that differ from the simple matched circle pattern. Standard search algorithms designed to detect ordinary matched circles pass through this topology's signatures essentially without noticing them. Oliver Philcox, commenting on this finding, noted that there are many possible ways the universe could be topologically connected, and that eliminating them remains genuinely difficult. That observation contains an important insight. Every time cosmologists announce constraints on some version of a wrapped universe, they mean specifically the version they actually tested. The full catalog of possibilities contains far more configurations than any individual search has addressed. Analogous results emerged for another twisted variant, a version where the connecting rotation is 90 degrees rather than 180 degrees. This topology also survived the existing constraints, and for related reasons. The phase, relationships it creates between different spatial regions differ sufficiently from simple translational symmetry that standard searches are blind to it. These were not marginal cases invented to preserve a failing theory. They were members of a mathematically complete enumeration of all possible geometrically flat universes. If the universe is flat, which the evidence strongly supports, then all 18 of these configurations represent legitimate physical candidates. Most had received no meaningful observational scrutiny. The compact team was working systematically through the entire catalog, and what they were building to accomplish this amounted to a fundamentally new way of listening to space itself. In 1966, a mathematician named Mark Cox published a paper bearing one of the most memorable titles in his discipline. He called it, "Can One Hear the Shape of a Drum?" The question seemed playful on its surface. The mathematics beneath it was rigorous and profound. Drums of different shapes support different characteristic vibrational modes. A rectangular drum resonates differently from a circular one. A triangular drum generates an entirely distinct frequency spectrum. The question was whether those frequencies alone, the sound profile alone, contained sufficient information to reconstruct the physical geometry of the instrument. The answer, as it turned out, was largely yes, with certain subtle exceptions. Decades after Cox's paper appeared, the compact collaboration recognized that identical reasoning applies to the cosmos. Every topology possesses a unique set of permitted frequencies, the oscillation modes that can exist within the finite space it defines. A three-torus universe supports waves of particular sizes and orientations, determined by its fundamental domain dimensions. A dodecahedral space supports entirely different waves, shaped by its pentagonal faces and their connecting rotations. A simple, infinite flat universe, by contrast, supports every frequency without restriction. Each topology is a distinct instrument, and the cosmic microwave background is the music that instrument has been generating since the universe was 380,000 years old. The compact team constructed what they call correlation matrices. For any given topology with a specified size and orientation, you can calculate mathematically what the cosmic microwave background should look like. Specifically, you can predict the statistical correlations between temperature fluctuations at different angular positions across the sky. Different topologies produce different correlation patterns. Some suppress correlations at large angular separations. Others generate correlations between points on opposite sides of the sky. Twisted topologies produce correlations that exhibit rotational relationships between sky patches, in ways characteristic of their particular twist angle. Once you have the predicted correlation matrix for a topology, you compare it against actual measurements from the Planck satellite. If the topology matches the real universe, the agreement should be clear and statistically robust. If the topology is wrong, the discrepancy appears plainly. Execute this comparison across the full catalog of possible flat topologies, and you have a systematic survey that was computationally impossible only a decade ago. The team extended this methodology in multiple directions. They analyzed orientable topologies, where a traveler moving through the space returns to the starting point with original orientation preserved, and non-orientable topologies, where completing the journey leaves the traveler mirror reversed with left and right exchanged. They derived predictions for how different topological structures would affect the polarization patterns in the cosmic microwave background, not just the temperature fluctuations. They implemented machine learning approaches, training computational classifiers on synthetic universes with known shapes, teaching the algorithms to recognize topological signatures, the same way an image recognition system learns to distinguish handwritten characters. Craig Copy returned repeatedly to the large angle correlation anomaly in the cosmic microwave background. The empirical fact that temperature fluctuations display essentially no correlation for angular separations exceeding 60 degrees, when the standard model predicts substantial correlation extending all the way to 180 degrees. A finite universe with a compact topology would naturally suppress the oscillation modes responsible for those large-angle correlations, cutting them off in a pattern that matches what telescopes have been measuring for decades. The musical metaphor had genuine mathematical substance. The universe was playing a composition in which specific notes were absent. The compact methodology was designed to determine what shape of instrument produces exactly that particular silence. What the James Webb Space Telescope was about to add would make finding that answer considerably more urgent. Something had gone fundamentally wrong in the early universe, and it was becoming impossible to ignore. The James Webb Space Telescope was constructed to peer farther back in cosmic time than any previous instrument in history, to push observation all the way to the very first galaxies that emerged from the darkness following the Big Bang. The standard model generated specific, confident predictions about what those primordial structures should look like. Small, irregular, chaotic in appearance, sparsely distributed, the seeds of future structural complexity rather than finished products. The cosmos, just a few 100 million years after the Big Bang, should resemble a preliminary sketch, not a completed work. Webb directed its gaze toward that era and found something that looked disturbingly complete. The standard picture of galaxy formation is grounded in decades of theoretical development and observational support. Galaxies grow hierarchically. Smaller gravitational concentrations form first, then combine over hundreds of millions of years into progressively larger assemblages, like villages gradually merging into towns and eventually into cities. The very earliest universe should contain only small, chaotic protogalaxies, the seeds that will eventually mature into the grand spiral and massive elliptical structures visible in the relatively nearby cosmos. The galaxies Webb found at the greatest accessible distances looked nothing like seeds. They resembled fully grown trees. One galaxy is positioned at such an extreme distance that its light traveled 430 million years to reach the telescope, having formed when the universe was a tiny fraction of its current age. Its stellar mass, the total combined weight of all the stars it contains, substantially exceeds what the models indicated should be achievable at that epoch of cosmic history. Dozens of additional galaxies confirmed at comparably extreme distances tell the same story. Their masses, their structural organization, their apparent developmental completeness, all of it contradicts the standard timeline for how matter assembles under gravitational attraction. Researchers proposed that perhaps these early galaxies had converted their available gas into stars with extraordinary efficiency. The numbers came back unfavorable. Reaching the observed masses within the available time would have required converting essentially all available gas into stars at nearly perfect efficiency, something that violates the established physics of star formation under any conditions currently understood. A 2023 paper by Alistair Graham and collaborators stated the situation without diplomatic softening. Such massive galaxies, the paper noted, simply do not have sufficient time to form within the standard cosmological model. These observations represent a significant challenge to standard cosmology. Michael Boylan Colchin at the University of Texas at Austin performed independent calculations and arrived at the same conclusion. Some of what Webb was finding required physical conditions that the standard model simply does not permit. Something fundamental in the theoretical framework was generating incorrect predictions. This was not a fine-tuning problem. The early universe was assembling massive galaxies faster than the laws of physics as currently formulated should allow. No incremental adjustment to the existing framework would mend the discrepancy. Why this mattered for the shape of the universe would become apparent over time. Galaxy formation occupies one domain of physics. Cosmic topology occupies another. But when a foundational model fails in one domain, everything constructed on its assumptions becomes suspect. And the standard cosmological model carried within it a very specific set of inherited geometric assumptions that had never been independently verified, but had propagated silently through the theoretical framework from its inception. The problem extended deeper than anyone had yet appreciated. They appeared in the Webb data as compact, intensely red smudges scattered across images saturated with the light of the early universe. Nobody had predicted them. No existing theoretical framework had reserved a place for objects of this kind. Astronomers began calling them little red dots, a casual label for objects that turned out to carry substantial theoretical implications. The little red dots are supermassive black holes. That identification became clear relatively quickly from their spectral properties. Supermassive black holes reside at the centers of most large galaxies in the nearby universe, so their existence is not inherently surprising. What makes the little red dots deeply problematic is their timing and their scale. They are actively accreting matter at furious rates only 600 million years after the Big Bang. And they are enormous, far more massive than they have any right to be given the brief interval the universe had existed when they are observed. Astronomers have established a reliable empirical relationship between the mass of a central black hole and the total stellar mass of its host galaxy. The black hole constitutes a small fraction of the stellar mass. This correlation appears to emerge from the co-evolutionary feedback between black holes and their surrounding galactic environments over billions of years. It is one of the most robust and consistently observed relationships in extragalactic astronomy. The little red dots demolish this relationship entirely. Their black holes outweigh their host galaxies by factors of 100 to 1,000 times compared to what nearby universe observations predict. The black hole grew faster than the galaxy enclosing it. In certain cases, the black hole appears to dominate the entire system, with the surrounding stars almost incidental to the structure. Then came a single discovery that sharpened the problem, more precisely than any preceding observation. A galaxy now designated Virgil was characterized by researchers at the University of Arizona in 2025 as a cosmological shapeshifter. George Reek, a pioneer of infrared astronomy who contributed to the design of Webb's own instruments, was unambiguous about what the telescope had found when he described this object. He stated that the James Webb Space Telescope had demonstrated that theoretical ideas about how supermassive black holes formed were essentially completely incorrect. That is not cautious hedging from a circumspect researcher. Rika has spent decades designing instruments to examine the universe at wavelengths invisible to human eyes. When he characterizes formation models as completely wrong, the weight behind that assessment is substantial. Inflating a black hole to that mass in a universe that young requires surpassing the physical limits on how rapidly infalling matter can be consumed before radiation pressure halts. Accretion entirely. Standard astrophysics provides no comfortable mechanism for what Webb was observing. The proposed alternatives, including black holes that formed directly from collapsing gas clouds rather than from dying massive stars, require modifications to conditions in the early universe that propagate outward through the entire cosmological framework. Every adjustment proposed to account for the little red dots touches assumptions that extend into the broader theoretical model. Assumptions concerning dark matter behavior. Assumptions about the initial conditions from which all structure grew. Assumptions the cosmological framework accepted without scrutiny, and upon which everything else was subsequently constructed. The thread had been pulled, and what followed would reveal how deep the unraveling extended. The earliest galaxies in the universe were expected to be roughly spherical. Gravity acts inward from a central concentration of mass, drawing in gas and dark matter in an expanding sphere. Early structures might be irregular and disordered in detail, but standard models consistently predicted that the very first galaxies would lack significant elongation. The primordial cosmos should appear lumpy and compact, without the extended filamentary forms that emerge later as the cosmic web develops over billions of years. Webb examined the early universe and found something categorically different. A 2025 study led by Alvaro Pozo at the Donostia International Physics Center in Spain, with contributions from Rogier Windhorst at Arizona State University and a broader international team, analyzed the morphologies of early galaxies captured by the James Webb Space Telescope. The conclusion was striking. Many of these galaxies displayed strongly elongated filamentary morphologies. They were stretched out, extended along preferred spatial directions. They resembled early compact blobs far less than they resembled cosmic threads with no business appearing so early in cosmic history. The standard cold dark matter model could not generate these shapes in any of its simulations. In standard computational models, the earliest structures form in arrangements that do not reproduce the degree of elongation that Webb was observing. The discrepancy was clear and reproducible. One alternative framework matched the observations considerably better. Wave dark matter, also called fuzzy dark matter, is built on the premise that dark matter consists of ultralight particles so extraordinarily light that quantum mechanical effects operate on astronomical scales. These particles behave less like a collection of individual microscopic projectiles and more like a fluid governed by wave equations. Quantum pressure resists gravitational compression in ways that classical particle dark matter never experiences. generating structures with smooth central profiles and suppressed small-scale clustering. At large scales, this wave-like dark matter naturally organizes along quantum interference patterns, generating elongated filamentary structures of precisely the kind that Webb was documenting in the early universe. This finding carries implications extending well beyond the question of dark matter composition. If dark matter behaves as waves rather than classical particles, the primordial distribution of density fluctuations across the early universe is fundamentally altered relative to what cold dark matter predicts. The seeds from which all galaxies grow have a different statistical character, suppressed on specific scales in ways that cold dark matter never produces. The entire history of how large-scale cosmic structure assembles through time changes accordingly, and the power spectrum of those initial density perturbations is precisely the quantity that cosmologists use to constrain spatial curvature and search for topological signatures in the cosmic microwave background. A revision to the nature of dark matter that modifies the power spectrum does not remain confined to galaxy formation theory. It alters the input to every measurement the field uses to assess the geometry and topology of space. The discovery of elongated early galaxies therefore connected directly to the topology question in a consequential and non-obvious way. It represented another thread in the same larger fabric. When the dark matter model requires revision, the cosmological model requires revision with it. And a model undergoing revision cannot simply inherit its geometric assumptions unchanged from a prior version of itself. Something more fundamental than galaxy morphology was shifting. For years, two independent groups of astronomers have been measuring the same foundational quantity and obtaining answers that disagree by 4 to 5 standard deviations. The quantity is the Hubble constant, the rate at which the universe expands, describing how rapidly distant galaxies recede from us. It is one of the most basic numbers in all of cosmology. Both groups are rigorous. Both have published their methodologies in full detail. Both have validated their results through multiple rounds of independent verification. They continue to disagree, and the gap between them has not narrowed. The first group uses the cosmic microwave background. By fitting the standard cosmological model to the temperature fluctuation pattern in the ancient light, they derive a Hubble constant of roughly 67 to 68 kilometers per second for every million light-years of distance. This is the early universe measurement, anchored in physics from just 380,000 years after the Big Bang. The second group uses the cosmic distance ladder. They measure pulsating stars called Cepheid variables in nearby galaxies, calibrate those measurements against distances to exploding stars called supernovae, and use those supernovae as standardized distance indicators to measure the expansion of the present-day cosmos directly from observation. Their result settles at roughly 73 kilometers per second per million light-years, substantially higher than the early universe figure. This discrepancy carries the name the Hubble tension. At 4 to 5 standard deviations of statistical significance, it is large enough that in virtually any other scientific discipline, it would constitute a confirmed discovery of previously unknown physics. Something has gone wrong inside the model somewhere, and cosmologists have been trying to locate the source for years. One underappreciated dimension of this tension connects directly to the curvature of space. There is a well-documented geometric degeneracy embedded in the cosmic microwave background data. A closed universe with a slightly lower Hubble constant and a marginally elevated matter density generates temperature fluctuation patterns that are nearly indistinguishable from a flat universe with a higher Hubble constant and lower matter density. The two distinct physical scenarios appear essentially identical in the Planck satellite data. This means that the apparent Hubble constant extracted from the cosmic microwave background is entangled with the flatness assumption in a way that public discussions of the tension rarely acknowledge. Di Valentino and her colleagues argued explicitly that assuming flatness could be concealing a deeper crisis. A universe that is marginally closed, carrying the mild curvature that the Planck data alone suggests, would naturally yield a lower apparent Hubble constant from cosmic microwave background analysis. The local direct measurements, which carry no such geometric assumption, return the higher value. The tension between those two numbers could therefore reflect, at least in part, the fact that the universe contains geometric structure that the Standard Model is failing to account for. Non-trivial topology complicates the picture further still. Different topological configurations modify the effective power spectrum of the cosmic microwave background in ways that shift the fitted cosmological parameters, including the Hubble constant itself. A universe with a compact topology could appear to prefer a different expansion rate. The underlying expansion might be identical. The apparent discrepancy would arise from the topology, distorting the interpretation of the data within a framework that assumes no topology exists. The Hubble tension might be a crack propagating through the foundation of the Standard Model, or it might be a window into something altogether stranger than a simple parameter error. The Standard Cosmological Model has a formal designation: lambda cold dark matter. Lambda represents the cosmological constant, the energy density intrinsic to empty space that drives the observed acceleration of cosmic expansion. Cold dark matter is the dominant form of invisible matter, slowly moving particles that aggregate under gravity and construct the invisible scaffolding upon which all visible structure assembles. Together with ordinary baryonic matter, radiation, and the geometry of a nearly flat universe. These ingredients describe a framework that has successfully reproduced an extraordinary range of observations spanning decades of precision measurement. It is also increasingly a framework under siege. Every anomaly the James Webb Space Telescope has revealed adds weight to the same conclusion: galaxies too massive and too structurally mature in the first few 100 million years after the Big Bang. Black holes too large relative to their host galaxies at extreme redshifts. Morphologies that cold, dark matter simulations consistently fail to reproduce. A universe that assembled its large-scale structure faster than the standard timeline can accommodate. No individual anomaly is fatally conclusive by itself. For each separate discrepancy, a targeted modification, a parameter adjustment, or an invocation of new physics can be proposed in isolation. But the anomalies are arriving together, all pointing in the same direction, all indicating that something at the foundational level is generating systematically incorrect predictions. Modified gravity represents one class of response. If gravity itself operates differently at cosmological scales than general relativity predicts, the rate at which large structures form and grow is altered. Galaxies could assemble faster. Black holes could grow faster. But revising gravity leaves the curvature of space altered as well. A different gravitational law implies a different geometric relationship between matter, energy, and the shape of space-time. Curvature measurements derived within the standard gravitational framework inherit that framework's assumptions, and would shift their values if those assumptions are wrong. early dark energy represents another hypothesis. If an additional energy component was present during the universe's first few 100 million years, the expansion history preceding galaxy formation would differ from the standard account. The cosmic ruler used to interpret the microwave background would require recalibration. Recalibrating that ruler shifts the apparent Hubble constant, potentially closing part of the gap with local measurements. But early dark energy also alters the meaning of curvature measurements, because curvature is extracted from the same observational data using the same expansion history that is being revised. Wave dark matter changes the initial power spectrum of density perturbations, the same spectrum that topology searches use as their baseline for comparison. What unifies all of these possible extensions to the standard model is a single uncomfortable truth. Lambda cold dark matter is not simply a theory of galaxy formation or large-scale structure. It is a global framework connecting cosmic microwave background measurements to galaxy clustering measurements to the geometry of space. Every component connects to every other. When one element is wrong, the corrections propagate through the entire structure. D. Valentino and her collaborators had written exactly this conclusion. The flatness assumption, they argued, could be masking a cosmological crisis in which disparate observed properties of the universe appear mutually inconsistent. The universe was not waiting for a clean resolution. It was accumulating inconsistencies faster than any individual fix could absorb. And the most detailed map of the early universe ever constructed was about to add one more essential layer to the evidence. In June 2025, an international collaboration of more than 200 scientists released a catalog that redrew the three-dimensional map of the observable universe in a single document. The project was named Cosmos Webb. It was constructed from 250 hours of observation time on the James Webb Space Telescope, directed at a carefully selected patch of sky covering an area several times larger than the apparent disk of the full moon. The resulting catalog, led by Marco Castellano at the Cosmic Dawn Center in Copenhagen, contained the positions, distances, masses, and morphologies of 780,000 galaxies. It was the largest, deepest, and most complete three-dimensional survey of cosmic structure ever assembled. Every object in that catalog represented a data point in the ongoing dispute over what the universe actually looks like at its largest scales. Previous galaxy surveys had been powerful but limited in various ways. Ground-based observatories had mapped hundreds of millions of galaxies in the relatively nearby cosmos, but lacked the depth to probe the distances where the early universe's large-scale structure becomes most revealing. Webb extended that frontier dramatically. The Cosmos Webb catalog reached redshifts of approximately 7, capturing galaxies as they appeared when the universe was less than 1 billion years old, a small fraction of its current age of 13.8 billion years. What the catalog confirmed in the clearest terms yet achieved was the anomalous abundance of massive galaxies in the early universe. Smaller Webb surveys had already suggested this problem. Some skeptics had proposed that the early results might reflect incomplete data, statistical flukes from limited sample sizes, or subtle calibration errors that more comprehensive coverage would eliminate. The Cosmos Webb catalog, with its 780,000 objects distributed across a large, continuously observed region of sky, surveyed with uniform methodology, eliminated those objections systematically. Massive, organized galaxies existed in the early universe in numbers that the standard model cannot explain. The abundance was a feature of the cosmos, not an artifact of the survey strategy. But the catalog offered something beyond mere confirmation. By mapping the three-dimensional spatial arrangement of galaxies across an enormous volume at extreme cosmic distances, Cosmos Webb provided precisely the kind of data that the compact collaboration needed to extend its topological search, far beyond what the cosmic microwave background alone could offer. The microwave background provides a two-dimensional snapshot of the last scattering surface, a single shell of ancient photons carrying information from one specific moment in cosmic history. Galaxy surveys populate the full three-dimensional volume of space with information spanning a vast range of cosmic distances and epochs. A universe with a compact topology would imprint specific signatures in that volumetric data. Galaxies in one region of the survey would exhibit correlated patterns with galaxies in apparently distant regions, because the topology folds space so that those distant points are actually connected through the fundamental domain of the universe. These correlations carry geometric signatures determined by the size and shape of that fundamental domain, signatures that become more detectable as the survey volume and depth increase. With 780,000 objects extending to the depths that Webb could probe, the statistical power of a topological search multiplied enormously compared to any previous dataset. The question of cosmic shape had advanced beyond pure theoretical speculation. The data needed to answer it was arriving in quantity. The mathematical tools to analyze it had been constructed. The collaboration to execute the search was already at work. Whatever they might discover would transform our understanding of the universe we inhabit. The assumption concealed inside virtually every cosmological model is a significant one. Most scientists, when pressed, will acknowledge that they assume the universe is infinite. Space continues forever in every direction, never terminating, never bending back, expanding outward without limit. The assumption sounds clean, almost self-evident. But when you follow its logical consequences to their conclusion, the universe becomes something deeply troubling. An infinite universe contains infinite matter, infinite galaxies, infinite interstellar gas, clouds, infinite versions of every planet that has ever formed anywhere. And here is where the difficulty begins. If space extends infinitely and matter is distributed according to random quantum fluctuations, then every conceivable arrangement of matter must be instantiated somewhere. Given sufficient volume, every configuration, every combination of particles, every accident of physics that could occur will occur in infinitely many locations, infinitely many times. That includes you. In an infinite universe, there is not one instance of this specific moment. There are infinitely many identical instances. Somewhere, separated from you by a distance so immense that no signal could ever traverse it, an exact duplicate of you exists, experiencing these same ideas. Somewhere else, a version of you made a different decision last Tuesday. Somewhere else still, the configuration of matter produces a world in which you were never born. This sounds like philosophy. Physicists treat it seriously because the mathematics gives them no choice. The problem deepens when you ask a deceptively simple question. What is the probability of anything in an infinite universe? This is called the measure problem in cosmology. In an infinite space populated by infinite copies of every event, how does one calculate the likelihood of any specific outcome? How does one assign meaning to a probabilistic prediction when every result, however improbable, manifests infinitely many times? The mathematical framework collapses entirely. Physicists regard this as one of the most severe conceptual failures in modern cosmology, and it has no agreed-upon resolution. The problem exists only because the universe is assumed to be infinite. Then there is the Boltzmann brain. Ludwig Boltzmann, the 19th century Austrian physicist who constructed the mathematical foundations of thermodynamics, demonstrated that in any physical system with sufficient time available, random thermal fluctuations will eventually assemble extraordinary configurations of matter. In an infinite universe with infinite time, such fluctuations will eventually randomly generate something resembling a fully formed human consciousness, a disembodied mind floating in empty space, convinced that it perceives a genuine external world. These are called Boltzmann brains. An infinite universe generates infinitely many of them. The disturbing implication is that these randomly assembled observers vastly outnumber observers like us, who arose through ordinary cosmic evolution, which suggests by simple counting that you are statistically more likely to be a Boltzmann brain than a real one. No cosmologist actually believes this, but no one has cleanly resolved the paradox either. The infinity assumption also renders cosmology fundamentally non-predictive at the deepest level. Statistics cannot be conducted on infinite sets in a meaningful way. Probability requires a finite denominator. Physics, at its core, is the discipline of quantifying things, and an infinite universe dissolves quantification before it can begin. These are the consequences of the assumption that passes almost unexamined. An infinite universe looks elegant from a distance and reveals itself catastrophic on closer inspection. And here is what makes the search for cosmic topology so consequential. It offers a genuine resolution. A finite universe with a compact topology eliminates the infinity problem at its source. The measure problem evaporates. The Boltzmann brain paradox loses its logical force. Statistical reasoning becomes meaningful again. Physical predictions become possible again. The scientists searching for the shape of the universe are pursuing something far more important than academic curiosity about geometry. They are attempting to rescue the most fundamental cognitive tool humanity has ever developed, the capacity to understand anything at all. A finite universe, however, raises its own peculiar questions. And what it might look like from the inside is unlike anything you have likely envisioned. Invert the assumption. Suppose the universe is finite, closed, and folded back upon itself. Suppose it resembles the surface of a sphere more than it resembles an infinite plane. Something extraordinary then follows from elementary geometry, something that should genuinely stop you. Light would travel in closed paths. In a finite multiply-connected universe, a beam of light traveling in any fixed direction would eventually complete a full circuit and arrive back from the opposite direction. It would not collide with a wall. There are no walls. It simply traces the curvature of space back to its origin, the way a ship sailing continuously westward eventually returns from the east. The universe has no edge to encounter because it wraps around. Now, consider what this implies for everything we observe. Every object in such a universe would have multiple images. A distant galaxy whose photons had time to complete a full circuit of the universe would appear at multiple separate locations in the sky. The same physical object seen from different angles at different moments in its evolutionary history. The universe would become, as French cosmologist Jean-Pierre Luminet described it, a cosmic hall of mirrors. The same limited spatial region reflected and replicated in every direction, generating the convincing illusion of a vast and endlessly varied cosmos that is in reality a single finite chamber observed repeatedly from different vantage points. This is not speculation. It is a mathematically rigorous consequence of specific topological configurations. And the unnerving aspect is that we might already be living inside such a universe without any awareness of it. Consider what that would mean for every sky survey ever conducted. Every catalog of distant galaxies, every deep field image displaying thousands of objects distributed across the field of view. Some fraction of those objects could be the same galaxy observed at different stages of its development, from different directions, appearing as entirely separate structures simply because no one has yet determined where to search for the repetition. The observable universe might be dramatically smaller than it appears. The entire observable cosmos might be the same cosmic neighborhood photographed through 1,000 different windows positioned around the same room. Luminet stated it precisely. Physical space can be closed, small and multiply connected, yet produce the impression that the observed space is considerably larger. In such a universe, you would also be seeing your own galaxy somewhere in that vast array. Billions of years ago, when it was young and turbulent, before the stars that contributed to our planet's formation had ignited, a galaxy that will eventually be ours would appear somewhere in the deep field images, unidentified because it bears no resemblance to what it will later become. We have been photographing our own past and cataloging it as someone else's history. A finite wrapped universe also resolves the infinity problem. The total quantity of matter becomes finite, at least in principle. The Boltzmann brain paradox dissolves. The measure problem finds resolution. Physics regains its predictive power. But the finite universe hypothesis carries its own demand. If it is true, evidence must exist. The cosmic microwave background, the most ancient radiation we can detect, must carry structural fingerprints of the universe's shape. Those fingerprints would appear as matched statistical patterns, identical temperature fluctuation sequences occurring in separated regions of sky, because they represent the same physical location observed from different directions. That test is being actively conducted right now. The results remain inconclusive, but the signals that have emerged in the data are stranger than anyone anticipated, and one of them looks like a scar from something that occurred before our universe came into existence. Inflation never truly ceased. That is the unsettling implication of the most widely accepted extension of inflationary cosmology. In eternal inflation, the mechanism that drove the extraordinary expansion of space in the universe's first moments did not shut down cleanly. It continued, and it continues still, in regions of space so remote from us that no signal could ever traverse the distance separating us from them. Space keeps generating new volume incessantly across an endless expanding landscape. Occasionally within that landscape, a localized region of space stops inflating. It becomes a bubble, a domain where the laws of physics settle into stable values, where matter can exist, where stars and galaxies can form and evolve. Our universe is one such bubble. Other bubbles exist elsewhere, each with its own physical constants, its own geometry, its own complete history unfolding in absolute isolation, separated from every other bubble by an expanding void that no physical process can ever bridge. This is not established scientific fact. It is a theoretical framework grounded in rigorous mathematics, taken seriously by some of the most careful cosmological thinkers working today. And it connects to the shape of our universe in a way that is difficult to set aside. If other bubbles exist, they can interact gravitationally with ours. Not often, the probability at any finite moment is small. But across infinite time in an infinitely expanding landscape, such encounters occur. And when two bubble universes collide, the impact leaves a permanent mark. The mark would be preserved in the cosmic microwave background. It would appear as a circular disk-shaped anomaly, a region where the ancient photons look subtly different from the surrounding background, where the temperature pattern has been disturbed in a geometrically precise manner. Researchers Stephen Feeney, Matthew Johnson, Daniel Mortlock, and Hiranya Peiris worked out the mathematics governing bubble collisions in 2011. Their models specified what such collision scars should look like in detail. Now recall the cold spot, that 5-degree circle in the southern sky, cooler than its surroundings by 150 microkelvins. It persists in the data unexplained, surviving every analysis, resisting every mundane physical accounting. The supervoid hypothesis cannot fully account for it. Systematic instrumental errors have been ruled out through repeated independent examination. It is real, and it remains strange. One possibility stays on the table. The cold spot is a scar, a physical mark left on the fabric of our universe by a collision with another bubble universe, another cosmos that made contact with ours in the earliest moments of existence, and then departed forever. The temperature anomaly would represent the preserved echo of that encounter, recorded in the oldest light accessible to observation. If that interpretation is correct, then we have already observed indirect evidence for the multiverse. Not proof, but evidence. A signal that has sat in plain view for decades, classified as an anomaly, waiting for the theoretical framework that can properly explain it. The shape of the universe and the existence of the multiverse are bound together within this single unresolved question. A finite bubble with a specific topology implies the existence of other bubbles. Scars in the primordial radiation imply collision events. And the cold spot, still without a satisfactory explanation after more than 20 years of study, sits in the data like a question mark stamped into the earliest physical record of reality. Whatever produced it suggests our universe is not alone in some genuinely profound sense. And that changes the nature of asking about the shape of the space in which everything we know exists. Max Tegmark, the Swedish-American physicist at the Massachusetts Institute of Technology, developed an idea that sounds like science fiction and carries the intellectual weight of a hammer. He named it the quilted multiverse. The logic originates with a single assumption. Space is infinite. If space is infinite, and matter is distributed according to quantum mechanical processes with random local variations, then every possible arrangement of matter must be instantiated somewhere. The number of ways to arrange particles within any finite volume is itself finite. Given infinite volume, every such arrangement recurs. Not merely approximately similar arrangements, but exact reproductions down to the last particle. This means there exists a region of space at some incomprehensible distance where every particle in your observable universe occupies precisely the position it occupies here. Every galaxy is in the same location. Every atom is in the same configuration. Every thought occurring in every mind is the identical thought. That region constitutes, for every practical purpose, another you. And beyond it there are infinitely more. The quilted multiverse is not a separate dimension. It is not another universe in any exotic sense. It is simply the mathematical consequence that an infinite universe with random initial conditions guarantees. The multiverse in this model is nothing more than the remote reaches of the same continuous space you have always occupied. Here is the decisive implication. A finite, wrapped universe dismantles this logic entirely. If space is not infinite, if it closes back on itself at some definite scale, then the quilt is not an endless expanse. It is one patch, one chamber, one finite arrangement that does not repeat because there is no infinite space in which repetition could occur. Copies of you do not exist because there is no spatial volume available for them. The universe is a single, closed, unrepeatable configuration. Finding evidence for a compact multiply-connected topology would rule out the quilted multiverse. It would establish that you are not duplicated anywhere, that this particular arrangement of matter, this specific moment, these specific thoughts arising in this specific mind, are unique in the entirety of physical reality. They occur once and only once across everything that exists. That is either profoundly unsettling or profoundly beautiful, depending on your disposition toward such things. The two possibilities, infinite and self-contained versus finite and wrapped, lead to entirely different accounts of what existence fundamentally is. In an infinite, flat universe, every story has already been told infinitely many times, and will be told infinitely many more. In a finite, wrapped universe, every story is told exactly once, inside one small room that only appears vast because the mirrors have been positioned with extraordinary precision. And there remains a third possibility that the available data will not yet permit dismissing. The universe could be finite, but still large enough that its topological structure lies beyond the reach of any instrument we could ever construct. In that scenario, the quilt might contain copies of you, but they reside behind a horizon permanently inaccessible to any form of observation. The singularity of this moment might be an illusion sustained by the limits of what we can see. That is the genuinely maddening edge of the question. A discovery that could rank as the most profound in human intellectual history might also, in certain scenarios, be permanently inaccessible. But the next decade arrives with instruments that could change this assessment, and they are closer to operational readiness than most people recognize. The equipment being assembled right now was designed with precisely this question in mind. Lightbird is a satellite mission developed through a collaboration between the Japan Aerospace Exploration Agency and the European Space Agency, planned for launch around 2028. Its name stands for Light Satellite for the studies of B-mode polarization and inflation from cosmic background radiation detection. The mission will measure the polarization of the cosmic microwave background with sensitivity an order of magnitude beyond anything currently operational. Polarization patterns in the primordial radiation encode information that temperature maps cannot access, and certain topological signatures appear only in the polarization data. Lightbird is, among other things, a shape of the universe detector. On the ground, CMBS-4, the Cosmic Microwave Background Stage 4 experiment, is taking shape. It represents an array of ground-based detectors operating at microwave frequencies that will improve on every previous measurement of the background's temperature and polarization simultaneously. The angular resolution, sensitivity to faint signals, and sky coverage will all surpass previous experiments by significant margins. If subtle topological signatures exist in the ancient light that current instruments have not detected, CMBS-4 is designed to find them. Meanwhile, Euclid has already launched. This European Space Agency telescope, placed in orbit in 2023, is currently constructing the most detailed three-dimensional map of the cosmic large-scale structure ever attempted, covering a region spanning 15,000 square degrees of sky and extending to a redshift of roughly 2. Euclid is building the most complete picture of cosmic structure ever assembled, a full three-dimensional accounting of how matter clustered and organized over the past 10 billion years. A finite wrapped universe would imprint specific repetitions in this map, patterns in the galaxy distribution with no alternative natural explanation. The Nancy Grace Roman Space Telescope, planned for launch around 2027, will conduct deep infrared surveys complementary to Webb's observations. Together, they will provide the most detailed and temporally extended view of galaxy formation in history. SphereX, a NASA all-sky spectroscopic mission, will measure the redshifts of hundreds of millions of galaxies, providing the topological search with a statistical dataset of a scale and completeness previously unimaginable. Each of these instruments represents a new observational capability aimed at a question that has persisted since Aristotle first posed it. Each generates a new category of data that the compact collaboration has already begun preparing to analyze. The searches that failed in earlier generations failed partly because the available data was insufficient, and partly because the computational tools were too slow. Both of those barriers are being removed simultaneously. The same decade delivering these new telescopes also delivers machine learning techniques capable of evaluating millions of possible topological configurations in the time that earlier methods required to examine a handful. What was computationally infeasible 5 years ago is now routine. What is routine now will be trivially achievable in 5 more years. The era of actually answering this question has not merely arrived on the horizon, it has already begun. And what the compact collaboration intends to accomplish within this era extends further than any previous attempt at the problem. The compact team, roughly 15 scientists distributed across 7 countries, have never been content to search only where the observational conditions are most favorable. Earlier topology searches focused on the most elementary compact spaces, with the 3 torus being the most natural starting point, and searched for circles in the cosmic microwave background. When those circles failed to appear at the predicted scales, many researchers concluded that compact topology had been excluded. The compact collaboration examined that conclusion and found it inadequate. The simple 3 torus is excluded if its scale falls below the observable horizon. That constraint is real and established. But topology is not a single hypothesis. It encompasses a vast mathematical landscape of distinct possibilities. 18 distinct flat topologies exist. Hundreds of spherical topologies remain, and the compact team demonstrated in their Physical Review Letters paper of April 2024 that most of these had never been subjected to serious observational testing. Several of the exotic flat topologies, particularly the twisted tori in which opposite faces connect after a 180-degree rotation, survive all existing constraints even when their characteristic scale is far smaller than the observable horizon. They remain viable candidates. They have simply never been rigorously tested against the available data. Yashar Akrami, leading the mathematical analysis from the Instituto de Física Teórica in Madrid, stated the group's ambition plainly in conversations with science writers. The collaboration will either identify the topology of the universe or establish that the universe is sufficiently large that its topology cannot be detected with any technology currently available to us. Those are the only two acceptable outcomes. Everything in between represents insufficient effort. The collaboration's next phase will extend the search to spherical topological configurations, including the Poincaré dodecahedral space that Luminet originally proposed in 2003. This is the soccer ball universe with its 12 pentagonal faces, opposite faces connected after a 36-degree rotation, and a characteristic scale sitting at approximately 80% of the observable cosmos. That search was first attempted using early Wilkinson probe data, and the results remained contested for years. Compact will revisit it with full Planck data and methodologically superior techniques. The most powerful expansion of the search, however, will exploit the galaxy survey data. The cosmic microwave background delivers a two-dimensional snapshot of a single surface. Galaxy surveys populate the full three-dimensional volume of the observable universe with data across a vast range of cosmic distances and epochs. The Euclid, satellite, the Roman Space Telescope, and the SPHEREX mission will collectively supply the volumetric data that makes topological detection genuinely achievable, rather than merely theoretically possible. In a compact universe, the three-dimensional galaxy distribution carries identical topological fingerprints to those encoded in the ancient light. Specific correlations between galaxy positions, separated by very precise spatial distances, would recur throughout the survey if the universe wraps. Compact has already begun developing the statistical tools required to identify those correlations when the data arrives. Beneath all this mathematical machinery lies a collection of anomalies in the oldest light ever observed. Anomalies that have refused to dissolve through every upgrade in data quality, and that a compact topology would explain not as statistical coincidence but as inevitable physical consequences. The ancient light has been transmitting a message for decades. When the Wilkinson microwave anisotropy probe mapped the cosmic microwave background in the early 2000s, physicists immediately noticed that the largest features in the map were behaving anomalously. The quadrupole and octupole, the two longest wavelength patterns in that primordial light, were far weaker than any version of the standard model predicted. They also pointed in aligned directions, within 11 degrees of each other. A coincidence so improbable under standard assumptions that researchers named it the axis of evil. Then the Planck satellite arrived with superior instruments, and the anomalies did not diminish. They sharpened. The alignment persisted. The large angle correlations remained suppressed. The cold spot maintained its position. A hemispherical asymmetry became apparent, confirming that the universe looks measurably different in one half of the sky compared to the other. Gabriel Young, Nabila Aghanim, and collaborators confirmed in their 2024 paper in Astronomy and Astrophysics that these anomalies appear at a level found in typically less than 1% of simulated maps based on the standard cosmological model. Less than 1%. This means that if you generated 1,000 computer universes following standard physics and examined each one carefully, fewer than 10 would reproduce what we actually observe in the real sky. Craig Coppey of Case Western Reserve University, a founding member of the Compact collaboration, explains the connection to topology through a single precise analogy. A taut guitar string can only vibrate at wavelengths up to twice its own physical length. Notes with wavelengths longer than the string simply cannot exist on it. A finite universe operates by the same physical logic. It cannot support fluctuation modes larger than its own spatial extent. If the universe folds back on itself at a scale approaching the observable horizon, large-scale correlations would be suppressed above a specific angular threshold. They would fall effectively to zero. And that is exactly what the measured data shows. The angular two-point correlation function of the cosmic microwave background drops to zero at angular separations exceeding roughly 60 degrees, precisely where a compact universe of appropriate dimensions would cut it off. In a standard infinite universe, this constitutes a profound and unexplained mystery. In a finite wrapped universe, it represents the expected observational signature. The universe is revealing its walls in the only manner that walls transparent to direct observation can disclose their existence, through the notes they prevent from being played. The axis of evil alignment follows naturally from the same physics. In a compact space, the largest surviving fluctuation modes align with the underlying geometry of the topological structure itself. The universe carries a preferred orientation encoded in its shape, and the ancient radiation preserves it. The hemispherical asymmetry, the cold spot, the missing large-angle power, all of them cease to be mysterious anomalies requiring ad hoc explanation and become instead the inevitable consequences of inhabiting a finite, curved, and multiply-connected space. The oldest light in existence is not malfunctioning. It is a transmission. And the transmission has been sitting in the data all along, waiting for the correct question to decode it. Here is what the universe might actually look like when the picture comes into focus. Begin with what measurement has established. The local geometry is nearly flat, consistent with Euclidean space to within 0.5% across every precision measurement ever conducted. Triangles drawn between galaxies sum to 180 degrees. Parallel lines do not measurably converge. The curvature parameter sits close to zero in every combined analysis of cosmic microwave background and galaxy survey data. But the word local carries an enormous amount of weight in that statement. When Planck data is analyzed in isolation without supplementary galaxy survey inputs, the curvature parameter hints at something marginally closed. The omega k value settles at negative 0.012, plus or minus 0.010 in the most recent analysis. The central value consistently points toward closure, slightly, persistently. The hint has softened with improved data, but it has never vanished entirely. Now incorporate the global picture. The anomalies in the primordial radiation point toward a universe possessing a characteristic spatial scale close to the observable horizon. The compact collaboration has identified several topological configurations that remain fully consistent with all existing observations. The Poincare dodecahedral space with its 12 pentagonal faces and volume, roughly 80% of the observable cosmos, naturally accounts for the missing large-scale power in the ancient light. Several twisted torus configurations survive constraints that eliminated their untwisted analogues. A collection of positively curved spherical topologies remain entirely unexamined. If the universe wraps, it does so at a scale close enough to the observable boundary that the wrapping manifests as detectable statistical signatures in the ancient light and potentially in the galaxy distribution, when forthcoming surveys map it with sufficient resolution and depth. The topology might be the soccer ball dodecahedron that Luminet proposed. It might be one of the twisted tori that the compact team found still consistent after every search. It might be something not yet seriously considered, one of the numerous exotic configurations that computationally feasible searches have not yet reached. What would it feel like to live inside such a universe? Exactly like this. The local geometry would be indistinguishable from infinite flat space. No wall would ever appear. No boundary would ever make itself physically felt. Everything directly observable would look precisely as it does in the standard model. The difference would emerge only in the statistics, in the patterns, in the subtle repetitions of the same physical structures appearing at different angles and different cosmic ages, and perhaps in one detail more profound than any statistical measurement. Somewhere in the deep sky images already collected by the James Webb Space Telescope, somewhere among the hundreds of thousands of galaxies cataloged in the Cosmos Web Survey, there may be an image of our own galaxy. Young, turbulent, completely unrecognizable, assigned a catalog number, given a redshift, measured and filed away. The cosmic hall of mirrors may have already captured our reflection, and we simply have not yet identified the frame that holds it. The universe we might actually inhabit is finite, folded, and smaller than it appears. It only seems boundless because the mirrors are perfect. Picture the moment when a team at a computing facility working through a dataset from a next-generation cosmic microwave background experiment runs their correlation analysis for the 100th iteration. The code has been checked, re-verified, and examined again by people who genuinely do not want it to find something that is not really there. It finds it anyway. 6 pairs of circles in the ancient light, separated by precise angular distances, displaying identical temperature fluctuation patterns rotated by 36 degrees. The signal appears in one dataset, then in another. Then a third independent analysis conducted by a separate team on a different continent confirms it in a matter of hours. The universe is a dodecahedron. It wraps, it is finite. The size is quantified. The shape is identified. Or perhaps the signal arrives through a different channel entirely. The Euclid satellite's three-dimensional galaxy map, processed after years of careful observation, reveals that specific pairs of galaxies separated by exact co-moving distances are correlated in ways that standard cosmology cannot accommodate. The same galaxy imaged twice. The same cluster repeated at a different orientation and a different cosmic epoch. The fundamental domain of space identified for the first time, projected across the sky in the spatial distribution of light from a billion separate galaxies. Either way, the moment of discovery would be unlike any in the history of science. We would know that the universe is finite. We would know its size. We would know its shape, the specific mathematical object that describes the space in which all of existence unfolds. A question posed by Aristotle 350 years before the Common Era, refined across generations of mathematicians and physicists, transformed into something quantitatively testable by the 20th century, and finally answered. What is the cosmos? What is its geometry? And then the implications would arrive in cascading waves. Philosophy would need to reckon with a finite cosmos containing all of physical reality within a definite and calculable volume. Theology would confront a universe that is bounded, shaped, specific, one, mathematical object among the infinity of possible mathematical objects that could have existed and did not. The meaning of the word universe, defined since its first use as the totality of everything that exists, would require fundamental revision, because the totality of everything turns out to be a specific geometric structure with a name, a volume, and a measurable scale. Physics would confront the consequence that most of what we have been calling the observable universe is the same limited region of space examined over and over from different perspectives and different points in time. Every survey, every redshift catalog, every deep field photograph, all of it a series of reflections inside a closed, finite, self-referencing chamber of space. The discovery would also confirm something about humanity, that a species living on a small rocky planet orbiting an ordinary star in one galaxy among billions of reflections of the same small handful of actual galaxies looked at the oldest light it could observe, noticed that something was subtly wrong with the statistical patterns, and followed that wrongness all the way to the shape of everything that exists. That is what a discovery would mean, and it remains genuinely possible. The data has pointed toward it for decades. The instruments to verify it are being built right now. The honest position as of this precise moment in the history of science is that we do not know the shape of the universe. We know the local geometry is nearly flat. Every precision measurement of the cosmic microwave background, every survey of galaxy clustering, every combined analysis drawing on independent observational sources arrives at a universe that obeys Euclidean geometry to within a fraction of a percent. Triangles close. Parallel lines hold. The rules of high school geometry describe the space around us with extraordinary fidelity. We also know that the global structure, the shape of the universe considered as a single, complete object in higher dimensional mathematics, remains genuinely and profoundly undetermined. Local flatness is consistent with an infinite plane, a finite cylinder, a torus, a twisted torus, a Klein bottle, or 17 other mathematically distinct topological structures. Measuring curvature alone does not answer the question of global shape. That distinction between local geometry and global topology is the most consequential insight the study of cosmic shape has generated, and it remains underappreciated in the broader scientific culture. We know the cosmic microwave background carries anomalies, the quadrupole-octupole alignment, the missing large-angle correlations, the cold spot, the hemispherical asymmetry. Each of these persists at the level where fewer than 1 in 100 standard simulations reproduces it. Their simultaneous appearance in the same observational dataset has a probability under the standard model of less than 1/10 of 1%. They have survived every improvement in data quality. They sharpened rather than diminished with better instruments. They have refused for over 2 decades to disappear. We know that the James Webb Space Telescope has demonstrated the standard cosmological model is incomplete. Galaxies too massive for their age. Black holes disproportionate relative to their host galaxies. Morphologies that match wave dark matter predictions better than cold dark matter simulations. A catalog of 780,000 objects from the Cosmos Web Survey, confirming that the early universe is doing something the standard model did not anticipate and cannot explain. When a model is wrong in one domain, every assumption it carries must be placed under scrutiny. The assumption of flatness, the assumption of simple topology, the assumption that the universe extends without limit in every direction for all time. We know the compact collaboration has demonstrated that the overwhelming majority of possible topological configurations have never been examined. Exotic shapes remain entirely consistent with all existing observational data. The systematic search for cosmic topology has only just begun in any rigorous and comprehensive way. And we know that the instruments coming online over the next 5 to 10 years will extend that search to depths and precisions that were computationally inaccessible only recently. LightBird will measure the polarization of the ancient light with sensitivity no previous satellite could approach. Euclid and the Roman Space Telescope will map three-dimensional galaxy distributions across spatial volumes large enough to contain detectable topological signatures if they exist. SphereX will provide the statistical leverage of hundreds of millions of individually measured galaxies. The Compact team will execute the analysis. Glenn Starkman of Case Western Reserve University, who has devoted decades of his scientific life to this question, described the situation with appropriate precision. When it comes to the topology of the universe, he observed, we simply have no idea what to expect. That uncertainty is not a scientific failure. It is a scientific invitation. The shape of the universe is not a resolved question wearing the costume of open inquiry. It is genuinely, profoundly, and consequentially open. The answer is encoded in the oldest light we can detect and in the spatial distribution of every galaxy we have ever catalogued, waiting for the analysis that will finally extract it from the noise. Aristotle asked whether the cosmos has a limit. More than 2,300 years later, with the most powerful space telescope in human history in orbit, and the most sophisticated mathematical collaboration ever assembled actively working the data, the question endures. But for the first time in the entire span of recorded human thought, we possess the tools to answer it. The universe has a shape. The search for it has never been more serious, more technically capable, or more likely to succeed. We are closer to the answer than at any prior moment in history, and the answer, when it comes, will change the way every human being understands the space they occupy. The cosmos has been holding its secret for 13.8 billion years. It may not be able to hold it much longer,